Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone, and welcome. There are a lot of important issues about voting that have come about in recent years that we've seen, although maybe come about. Maybe it's not right to suggest they're new, but a lot of interesting technology issues have certainly come to the forefront. We have a lot of people in this area who have done some interesting work on voting, and a few visitors also. It was actually Seni Kamara's idea, the co-organizer of this workshop, who thought as long as we have all these people around, it would be really nice to get people together to talk about ideas and introduce some of the main points to people who may not have seen them in the past. So he and I spent some time and put things together. I think we've got an exciting list of speakers and workshop this morning. We'll have the morning set up as more of a formal, sort of structured background set of talks to give people a little bit of an introduction to the area. And then the afternoon is going to be more free-flowing, talking about some current work, some ideas, the ideas that it's more flexible and more of an exchange. To start off and give us a little bit of the background of what's happening, I'm very pleased that we have Paul Miller, who's the voting systems manager for the state of Washington, who's going to tell us, give us some grounding, I guess, about what it's really like out there in the world and how things work, some of the issues facing the public sector and some of the problems. Paul, in addition, has worked as a member of the Technical Guidelines Development Committee of the Election Assistance Commission. Have I got that right? Mm-hmm. Which is doing a lot of work now on trying to advance new requirements, new ideas into the landscape of voting systems. And he's going to tell us a little bit about some of what's going on. So welcome. Thank you, Paul.
Sure. Well, first of all, I was voting systems manager probably the last time Josh and I worked together. My title now is actually senior, which means I'm old, senior election technology analyst. And in addition to working for the Secretary of State for the past 10 years, before May 2000, I was working for King County Elections as their elections director, assistant director in charge of data processing. So I've had a lot of experience both at the local level in terms of putting voting systems together and fielding and getting them fielded, and then at the state level, looking at these systems and deciding which ones should be certified and which ones shouldn't be. And so to sort of give you a quick background on, in terms of Washington and voting systems, we have 4 different voting systems that are in use in the state of Washington. And it was originally 3 different vendors, and now it's kind of all up in the air. We have what used to be Global, then Diebold, then Premier, and now ES&S, with the DOJ suit requiring them to divest themselves of much of what they acquired from Premier. It's unclear what whose system King County belongs to. They're the only system in the county in the state that has that particular system, and then we've got about 12 ES&S systems, which also are fill in the oval. We have about 6 Sequoia systems, which are the connect the arrow system, and we have HART, which is a digital scan, fill in a box, and have it scanned, and the entire image gets scanned and stored and processed. And we have about 21 counties that are heart counties. I originally understood Josh to be asking me to talk with you about why election officials don't like end-to-end voting, which, just to prove that you guys are a lot smarter than I am, after thinking long and hard about that, I thought, I don't really want to do that, and called Josh, and he clarified that that's not what he was asking me to do. He was asking me more to talk about what the real-world problems are, as opposed to that we encounter as election officials, and probably in the process, I'm giving you the perspective that we tend to approach these issues from, which may well be a very different perspective than you're approaching these issues from. And again, from at least I can speak for myself, from my perspective, having worked in this area for 20 years, the challenges to ensuring the accuracy of election start primarily with human error. Either human error on the part of the voter or human error on the part of election staff. So one of the challenges is to build systems and create processes and an overall system that reduces that amount of error while also preserving the values that we have in our society about voting, which is to protect the privacy of the ballot and to ensure that one person, one vote, and ensure a way that, and one of the things I think that we're adding in terms of in being able to ensure public trust in the system is ensuring that all systems can be auditable. So that's number one. Number two, I think, is probably the human ballot interface issues. That there are a lot of problems that occur in that area that create inaccuracies. And then I would probably put machine failures way down at the bottom as and I make the comment that I think that a lot of things that get reported in the press as being machine failures and computer failures are in fact human errors and human and procedural processes that weren't followed correctly. I thought I'd talk quickly about a few national issues that and my perspective on them, and then I'd get down to Washington state specific because that's what I know. And Washington state, we're a little bit unique in that we in Oregon are the two states that virtually everyone votes by mail. We have almost no polling places, which means we also have almost no DREs and some of those kind of issues which other states are dealing with. But at a national level and as an infrastructure level issue, I think one of the big issues that we're dealing with is sort of the market size that we're dealing with and the funding sources that we're dealing with. As we were discussing last night, the market is small. It's not a market that a lot of companies want to get into, number one. And number two, it's not a market that's particularly a profitable one. I believe it was Forbes magazine had an article that I really thought nailed it on the head. And it referred to voting system salesmen as working as that type of salesman who works out of the trunk of their car. I think that's not completely accurate picture, but it really conveyed the idea that up until 2000 at least, voting systems were on a 40-year cycle. They were the IBM punch card machines and they were the lever machines, and those things have been around forever. And jurisdictions did not intend to replace them. And so until they wore out, broke down. And they were remarkably sturdy and hardy technologies. So one of the sea changes I think that's happened that hasn't really been fully worked out in our country yet is that after HAVA we have moved dramatically increased the amount of the personal computer type of technology that's being used. The life cycle on that is usually intended to be 3 or 4 years. It's going to be in the elections industry, I think, at least 10 years. And that 10 years is coming up sometime in 2012, 2013. And I don't know what jurisdictions are going to do at that point. Because the funding priorities tend to put election equipment down below the sewers and pothole fixes. And so some counties have already been able to start replacing their equipment and getting upgrades and that kind of stuff. And that's encouraging that there's been money available for that. But my experience has been that to get the funding that an elections department needs, something has to go drastically wrong in an election. And then we throw money at it. And then, and often without laying the kind of groundwork that really needed to be laid to throw the money at it. And then it's expected to last another 10 or 20 or 30 years. And one of the other aspect of this is that election officials are actually very resourceful in trying to make the technology that they have work. And it may require them a lot more work, a lot more staff than it ought to. The operation may be more expensive than it ought to be, but they make it work. And as long as it works, people don't see a need to change it. Recruitment of poll workers. In a state like Oregon and Washington, we don't have a problem with recruitment of poll workers. We don't have any polling places. But nationwide, that is a big problem. Trying to find people who are willing to work for 13 hours a day for minimum wage. What you get are people who are not working, and your best people that you can get are people who considered a civic responsibility, are willing to work 13 hours and be yelled at all day, and they tend to be retired and elderly. Some of the human interface issues, you're all familiar with the butterfly ballot. You may also be familiar with Sarasota County and the issues that came about why in that congressional race, where there's so many more undervotes on the DRE machines than they were in any other methods of voting. From my perspective, it was pretty obvious when I saw how the ballot was laid out and portrayed on the screen, as opposed to how it was laid out and portrayed on a paper. And on the screen, it was pretty obvious why the human eye would skip over that contest to go to the next contest. But when the culprit is considered to be, so the interface is an issue, if we understand it, we can solve it. If the machine is a problem, we can understand that and solve that. But when the thinking is that it's some diabolical computer program that is doing this, we can't get to the problem and solve the problem. And so part of getting public trust is making sure that I believe that our systems all have some means of accountability, which is why, as a member of the TGDC, I supported Ron Rivest's proposal for software independence. Not because I like the term software independence, it was more a matter of, I thought this brought in an assurance of a way of auditing our results and being able to say, if there's a question about our outcomes, that we can show whether or not the outcomes we produced were accurate outcomes. So take a minute to talk about Washington in particular, as I indicated earlier, we are vote by mail except for one county, and that's Pierce County. We have 39 counties with approximately 3.5 million registered voters. And they range from about 1,500 registered voters in a couple of our very small eastern counties to King County, which is about 1.2 million registered voters and about the 13th largest voting jurisdiction in the country. Combined with Pierce and Snohomish, which are both Puget Sound counties, that counts about over half of our registered voters in the state of Washington. Which means that 99% of the ballots that we count are paper ballots. And there's two principal means of processing paper ballots. One is that was what we call optical scan, and the other is what we call digital scan. In the optical scan world, what the machine is looking for is for a mark that is adequately bold. And how do you find what's adequately bold is an issue. But a mark that's adequately bold at a certain horizontal and vertical intersection. And if it's there, if they see it, it's added to the vote. And if it's not, then it's not. With the digital scan, the 21 Hart counties, what they're actually doing is taking and actually using off-the-shelf type of copy machines, Fujitsu's and RIJOH, and that kind of equipment to scan the entire ballot, and then the software is able to process the ballot in terms of being able to determine who voted and for what candidate, what contest. Since we're a voter intent state, the challenge for us is that when we receive a ballot, that ballot be marked in a way that the machine can actually read it. Now, I think it's probably would be pretty obvious to all of you, because it's a smart bunch of people, that if somebody circles the name and doesn't fill in the response area, the machine is not going to see that as a vote. If they use what might not be quite so obvious is if they use the wrong kind of ink, or use pencil instead of ink, or vice versa, depending upon which technology you're using, the scanner's not going to pick it up. And so we have a pre-inspection after they've been divided, after the identifying aspect of the packet has been separated from the ballot end of the packet. We unopen the ballot end of unseal that ballot end and pull out the ballot and take a look at it. And the staffs that are there are trained to recognize what will read in the optical scan reader and what won't, and what won't, they have to duplicate to another ballot. So that's the process there. What kind of impact does that have? Well, one, what I've illustrated is that within a vote by mail environment, we have less control over the utensil that the voter is using to mark their ballot. What we also don't have in that environment are means of providing immediate feedback to the voter. At the polling place, if you're using a DRE, the DRE immediately gives you feedback as to what it thinks your touch meant. And if it doesn't respond the way you think it should have, you try again, or you try something else. You try not to put your finger and drag your finger down the screen, or touch your screen with your palm of your hand, or do some of the other kinds of things. And sometimes there's calibration issues, so if you actually mark the candidate below or just a little bit below where you think you should be touching or above, you'll find that it finally will accept your vote the way you intended. There are some real machine-human interface issues in DREs that need to be dealt with, that need to be better than what they are. But it isn't, I don't believe at all, any diabolical type of issues. It's this issue that, ironically, because a voter has that immediate feedback and they immediately see that the feedback is wrong, interpret that as diabolical, whereas interestingly enough, in a state like New York, which still has lever machines, we've got people fighting against having DREs who want to keep lever machines, where it is very well documented that the lever machines have a lot of problems, but you don't know it because you don't get the feedback. So the human interface on the DRE needs to be dealt with and improved. And we need a means of being able to audit that process so that we can establish that, in fact, that the voter had the opportunity to see how the machine interpreted their touches and that their touches were counted in the way that the machine understood their touch. We have, on top of that, in terms of the difference between absentee balloting and poll balloting, is that we have a signature requirement that we have to be able to match their signature against the signature on their original registration form, which means that a certain number of people whose signatures who change over a period of time wind up getting their signatures rejected. We have a process to try to contact them, get them in, get their signature updated so that we can get their ballot counted. But we still probably have somewhere in the range of 1%, maybe two, who get rejected on that kind of basis. A thumbprint has the potential for fixing that problem, I think, yeah. And we've been talking about that may be the technology of the future as far as how we would do this authentication process. As we discussed last night, at our dinner, we also have a bit less control over the voting environment, which opens up the potential for other issues like coercion, which in the years that we have been using that in this state and in Oregon, we haven't gotten any reports of that, but it may be a very difficult issue to get to. Another issue that is difficult for us is the concept of access for people with disabilities. We're required to have one DRE at the county site for people with disability issues. It presents problems for people with disabilities to get to this one location in the county. We are working with ways of getting the equipment to them so that they can vote. We're also looked at ways, including this past fall, where Franklin County, when they send out their absentee ballots, also made an online ballot available where if you typed in the ballot code, which is not anything unique identifying them, simply what style of ballot, type it in, they were able to vote online and print that out and send it back. Helps people who have it's easier for them to hear something than it is for them to see it. It's going to help them.
Why is it voting online and printing rather than downloading an app, voting locally and printing, so no information leaks out.
Well, I believe that's essentially the way that worked. But even in that loading down the app, it was important to us that that the system couldn't identify who was doing the voting. That the only thing that they needed to provide was, and how am I doing on time, Josh? That the only thing they needed to provide was what style of ballot they were going to vote. And so they went through, clicked their thing. They were also able to click and get the voter pamphlet statement of the candidates and the picture and all of that kind of stuff. And if they had the equipment on their computer that would read them to it, JAWS, it would read it to them, and so forth. Not a perfect solution, though. You still have to be able to see well enough to make a signature on the oath. You still have to be able to fold that ballot up and insert it into an envelope, and then insert that envelope into another envelope and send it back. Audits and recounts. I think in terms of our work in that area, one of the things I'm proud of is Washington State's rules on recounts, which is that if the apparent winner and the apparent loser are less than 0.5% different, there's a automatic state-funded or county-funded, government-funded recount. And if that difference is less than 0.25% or 0.25%, it is automatically hand recounted. And those hand recounts are done in units, basically the precinct units, so that after the humans do their count, we can compare that with the machine count. And very often we'll find that we pick up errors in that process, like a ballot from another precinct got into this batch of precinct ballots. Or they didn't pick up that one of the ballots was an overvote, and so they counted it for one of the candidates. Or they just flat out miscounted it. And so we can send it back, have another team count it, and try to make that process as accurate as we can make it. Human counting is not a very accurate process, I can tell you, based on my experience with that. In terms of the audits, we provide that a 4% audit on the DRE equipment that's used. That means that 4% of the equipment that's used, they have to pull the tape and count that against the results they got. Now, in our state, again, the only use that it's used for is for disability access. In many counties, nobody votes on it. Pierce County, because they have so many still have so many polling places, probably has the highest numbers of those currently. And then we also provide what used to be parties could call for a count of 3%, I shouldn't say, of 3 precincts at random that they picked. We would hand recount and match that against the computer count. That's been increased to 6 batches. And here's the reason why. The ballots come back, when we have polling places, the ballots come back grouped by precincts or grouped by a polling place. It makes it easier to sort out the ballots. But when they're coming in daily, they're coming in just as they come in the mail. And so you may have a batch, and that batch may contain 50 different precincts from all over the county. So what we... I'm sorry?
With different ballot styles?
With different ballot styles and with... Yes. Yes.
Mailboxes, have the post office do the sorting? So if each precinct has a mailbox?
Yeah. There are some levels of sorting that are done. I think right now King County is sorting into ledge districts so that at least they're grouped by ledge districts. But actually, if I understand some of the theory behind audits, having a distribution rather than having a concentrated precinct is a smaller groups that is more widely distributed is actually better auditing technique. And so the auditing the batches, and I can use some help here. You guys are a lot smarter than me, but that's sort of my understanding of some of the theory behind auditing. So in conclusion, I would make this comment that I would argue that what we have found in our experience is that despite all of these issues that I've raised, is that the process is remarkably accurate. And I would argue it based on our experience with the automatic hand recounts, where the difference is 0.25%. That we have never seen an election outcome change. I'm not saying the results don't change, the raw numbers don't change, but the election outcome change, except when the original difference between the candidates was minusculely small. And of course, we had exactly the perfect illustration in this state in 2004 of that. The original machine recount between Rossi and Gregoire was 50 votes, as I recall, in favor of Rossi, and it wound up after the hand recount to be about 122 votes in favor of Gregoire. Out of 2.9 million votes cast, that's something like a 46 ten-thousandths of a point difference. So, I would argue that in 99.9% of our contests, the process is accurate enough to come up with the right candidate in the end. But when you get into an election like that one, you've entered into where we have not been able to compress the margin of error small enough yet. And that margin of error is suggested in my opening, human error, both on the part of voters and election staff, design interfaces between the user and either the paper ballot they're using or the DRE equipment that they're using, and then finally, in some what my experience over 20 years is is relatively rare machine failure type of issues. And usually when the machine error, there's a machine error failure, it's identifiable and correctable before it's certified. So thank you very much for letting me have the time to talk with you.
Can you set up while we take a question or two? I guess I'll start off by asking, is there anything that you think the research community can do that will make your life easier or make the system more trustworthy somehow?
I'm not sure if this fits with a couple things I would respond to on that question. One is helping us understand better how we can get an audit that is a good audit, but that it's also a doable audit. And there's some push, and you have to understand too that there's some pushback from the elections community in part because we have these recounts, and they seem to suggest that the process is pretty accurate. And in Washington, we have these recounts. We probably have 2 or 3 of these mandatory hand counts every year, and a dozen or more of the machine recounts every year. So it's, I feel like over the years we've had a lot of testing and a lot of opportunity to review. The other, and I'm not sure that this fits into your area, but I've been pushing for common data formats. And I actually have a paper that I can make available to anybody who's interested that I presented to NIST last October. For the elections community, what I think it means partially is this. What we have in the marketplace right now is that if a county purchases vendor X's equipment in order to do central count, and they purchased that 15 years ago or 20 years ago, that's their vendor. Now they've got to add DREs on it, they've got to add poll site counters onto it. Where are they going to go? Well, who can market the equipment that's going to talk to their tabulation system, that can get the ballot layout from their ballot layout system and talk to their ballot tabulation system? It's going to be the vendor that they purchased their equipment from 15 years ago. So we're requiring these companies to get into areas that aren't their strengths, and we're tying companies down to products that the only reason that they purchased it is because it was what they could afford based upon the vendor that they've been using for the past 15, 20 years. So if we can get it in some kind of a common data format where the inputs into devices is defined and the outputs from those devices is defined, I think we can create a better marketplace. And we have some specific issues coming up now where we are trying to do more for our UOCAVA voters where mail doesn't work well. They don't, when you are in Iraq or Afghanistan, it's hard to get the ballot to you, and then it's hard to get the ballot back from you. And so we're looking at ways of at least delivering the ballot electronically. But we need some vendors to be able to work with the ballot layout systems so they know what ballots to send, so that the person can get the ballot printed out, mark it up, send it back. And we cut off at least one end of the transit time. Common data format.
Thanks again. In the interest of time, because I know Sanjit has to run, I'll skip the whole explanation of why we're fortunate enough to have him here today. Long story, ask me later. But anyway, Sanjit is on the faculty at UC Berkeley and does work in formal verification, models testing, and has done some work on voting machines, and he's going to tell us, give us a brief summary of it now.
Thank you. Thank you for inviting me here. I'm scheduled to give a talk next door at 11 o'clock, so this is going to be a very truncated version of that talk, packed into 10 or 15 minutes. So I apologize in advance if it's too rushed or not clear. But this is based on work that David Wagner and I and our students did, which was published at CCS last year. So the paper is on our website, and I can send the slides to anyone who's interested. Okay, so as the title suggests, this is about formally verifying and testing a voting machine. So the first, I want to start with a disclaimer. This talk is mainly about verification, and not about not about all the issues dealing with security. Verification is one issue, but it's not everything. For instance, we don't talk about securing the voting machine against tampering, for instance. So proving correctness of the voting machine design is necessary for security, but I understand that it's not sufficient. So also, this work is, I think, a very small first step. What we wanted to do was explore what we can do in the design stage to make verification and testing easier. And so we designed a voting machine from scratch in hardware using Verilog and synthesizing it to an FPGA. So what we tried to do was create a DRE. All of you are familiar with this, so I'll just go through it very quickly. So the setup for this talk is we want to verify the correct operation of a single voter session. So a voter session is a sequence of contests for president, senator, etc. Each contest is a choice of picking L out of K options. And at the end, so you can navigate back and forth between these contests, but at the end you cast, and that irrevocably casts your vote, your choices for all contests. So our contribution is that we show that you can combine formal verification with manual testing by a panel of human voters to prove correctness of a voting machine. And in this context, we're interested in proving correctness not just of the code, but also of the interface, of the human-computer interface. And so we implemented a simplified DRE in hardware, and we used verification techniques like model checking and satisfiability, solving, fast theorem proving. And one of the things that we do is we show that you can use a small polynomial number of tests by humans to augment the results of formal verification. Okay, so very briefly, I'll talk about why we have this combination of formal verification and testing. I'll have a couple of toy examples, and then I'll just state the main results and conclude. Okay, so let's look at testing. If you want to prove correctness of a design by testing, you need exhaustive testing, but in many cases you can't even do exhaustive testing because the test sequences have to be infinite. So as this quote by Dijkstra illustrates, testing is usually a way of finding bugs but not proving correctness. Formal verification, of course, can prove correctness, but it requires a formal specification. You have to precisely define the requirements. So some properties of the voting machine you can precisely define, like if the reset signal is set to 1, then clears the selection state for all contests. But what about voters' expectations? How do you formalize something like this, that if the voter presses what they think is the button next to the name Alice, and then sees the Alice highlighted, then the voter thinks that, okay, the machine has recorded my vote for Alice, right? And so how do you actually, you can't really formalize that. And so that's the challenge. It's hard to use formal methods for something like that. So to summarize this very quickly, formal methods can prove correctness of the DRE implementation, the code, but you can't formalize voters' expectations. On the other hand, testing by humans, if you have a representative panel of human voters, then you can argue that you've tested the interface, but then testing is not sufficient to prove correctness. So that's why we try to use both. So the approach is for precise properties that you can formally verify, we'll do just that. For voters' expectations, we'll use testing by a representative panel, and this combination, as we show and prove in the paper, makes testing sound. And from my viewpoint as a person who does formal verification, the cool thing was you can use formal verification to exponentially reduce the number of tests you need. And I'll say a bit more about this at the end. Okay, so what's the challenge for testing? I think the problem, that the reason why you can't do exhaustive testing is that you require infinitely many input traces. Input trace is a sequence of button presses that you would give to a human voter and ask them to test out. Okay, so here's an example. Okay, so this is a sequence. Each element of the sequence is separated by commas. So the sequence means initially that you have the empty set, which means that no candidate is selected. Then you have Alice, which says that the voter selected Alice. Then again you have empty set, which means that the voter deselected Alice. Then the voter selects Bob, and then goes back to empty set. So what it means is that the voter is toggling between Alice and Bob. And the voter can do this, in theory, infinitely many times. Okay? And so how do we know that there isn't some logic in the voting machine that after 1,000 such toggles will trigger some erroneous behavior, right? And so that's why you don't a priori, if you don't know anything else about the design of the voting machine, you can't tell how long you have to test it. So before I talk about how we use formal verification to address that problem, let me tell you about what we mean by correctness. And this is a notion that's common in the formal verification community, which is called trace equivalence. So the idea is that you have at the bottom there the implementation. So that's the hardware FPGA-based design that we did. And and then you have the model, the mental model that the human voter has in mind, right? And we want to show that the execution of the voting machine, the real execution, which I'll show down here, will match the execution in the voter's mind. And so the approach is, let's say initially the voting machine, the implementation starts in contest number 1. Okay, so that's what that is, contest number. And in contest number 1, you have no candidate selected. So then the voting machine display looks like this, where there are 2 options and neither of them is highlighted, which shows that no candidates are selected. And the human looks at that and says, okay, from the screen I understand that I'm in contest 1 and there are no selections. And then let's say the voter presses Alice, and then ideally the implementation must record this, that in contest 1 Alice has been selected. The implementation must output the display which highlights the button for Alice. And then the voter looks at that and gets feedback and says, okay, now the machine is in contest 1 and my selection of Alice has been highlighted, right? And so here you have a trace of what's happening inside the machine, and up there you have a trace of what's happening in the voter's mind. And what we want is those 2 should be equivalent. That's what trace equivalence is. So to give you a toy example, let's see how an interaction like this might happen. So let's say the voter looks at the screen and sees that nothing is highlighted, right? So inside the machine, you have the empty set, no selections made, and that's what the voter understands. Then the voter presses button 1, thinking that they're voting for Alice. The machine should record internally Alice, should highlight that, and that's what the voter sees. And now the voter keeps track of this fact that now, according to the voter, the machine has recorded the vote for Alice, and then you want to check that what the voter has in mind is indeed what's inside the machine, right? And so the approach we take to do that is, for every unique screen, we have a way, we ensure that you can press cast from that screen. You get, let's say, some record, maybe on paper, and then the voter compares what he or she has in her mind to what's on paper, and that's how they do this equality check down there. Okay, so now let me tell you about how we use formal verification to make testing easier. So the first thing that we prove formally on the code is that the voting machine transition function is a deterministic function of only those inputs that it should be of. For instance, the selection state is only a function of the selection state at the previous time point, the button that was pressed, and the contest number, and nothing else, right? And so that's what we mean by proving that the DRE is deterministic. The second thing we prove is that the output should be unambiguous. That is, each unique output screen represents a unique internal state. From just looking at the output screen, the voter should be able to tell what the contest number is and what the selection state is. Okay, and that corresponds to proving that the code is the output function, that the code that computes the output function is a one-to-one function of the selection state and the contest number. And then finally, we need to verify that the cast vote record accurately records the selection state at the very end. And so all of these things are properties that we can prove on the code using a combination of model checking and satisfiability solving. So now, given those properties that we prove, we have then come up with a set of coverage metrics for tests. That is, so we say that if you give a sequence of tests that satisfy these coverage metrics, then we have a theorem which says that you then get trace equivalence. And so here are the 3 coverage metrics. The first is what we call initial state coverage, which means that the machine starts in a valid state. So when the machine in the initial contest, before any selections are made, if you press cast right there, then you get back a record which shows that there were no candidates that selected in any contest. The second has to do with transition coverage. So every contest is a state machine. It's, you're in some state, and then you press a button and you go to the next state. And what we want to do is we want to cover all the transitions for the state machine for every contest. Okay, so that's what these two bullets are describing. And then finally, we have something called output screen coverage, which means that for every unique output screen, we check that the voter has an opportunity to check that their view of the state of the voting machine for that output screen is indeed what is recorded. Right? So you see an output screen, there's some internal selection state and contest number, there is something in the voter's mind, and we want to match that up. Okay, so so now what I showed you first was just the interaction of a voter with the machine for one contest. But if you have even two contests, so say in contest 1 you're selecting between Alice and Bob, A and B, and in contest 2 you have to select between Eve and Mallory, E and M, then you already have this blow up in the space of the number of options that there are, right? So here, for instance, the voter selected Alice and then went to the next context, which is what that label means, and then in second contest they selected Eve and went up there, right? And so that's what that path means. But they could have selected Bob and gone down here, or they could have selected Mallory from that state, right? So there's an exponential blow up as the number of contests increases. And so if we were naive about testing, we would have to test every path through this state machine. So to solve that problem, what we do is, again, we use formal verification, but this time we prove that the logic for one contest cannot influence the outcome in another contest. Okay, this is the independence property. And so if you can then prove independence of different contests, it's sufficient to test each contest separately. So all you have to do is, to test contest I, you just navigate, press next, go to contest I, and then test the transitions in contest I. Okay? And this is what I meant by talking about an exponential reduction in the number of tests. Instead of having to test every path in the picture that you had in the previous slide, now we only have to test the transitions within each contest. Okay? So conceptually, this is what the DRE looks like. You have a state machine for every contest. You have to cover the transitions within each box, but not paths across the boxes. Okay, so in the interest of time, I'll wind up. So there are 6 major properties that we need to formally verify, and these are also in the paper. And given that, then we have a theorem, which is also proved in the paper, which says that if the DRE satisfies these 6 properties, then if we have a test suite that satisfies our coverage criteria, and if it passes, then it means the DRE is correct. And if the DRE is correct, then the test will pass. Okay, and so so now if you have an election with n contests and k choices in each contest, and you're picking 1 out of k in each contest, then our approach requires k times n tests, whereas otherwise you would have to consider all possible combinations, which would work out to be k to the n. Okay, so there are lots of limitations and assumptions that we make. I think the previous talk mentioned support for people with disabilities, and this is something, of course, that this does not handle at all. We assume that the compiler we use from Verilog to Silicon is trusted, and so we make all these assumptions. So as I said before, it's a first step. But from the viewpoint of verification, I think it's a very interesting exploration in the use of formal verification and its combination with testing. Okay, so I will stop here. Thank you very much.
Questions?
Yes.
What about the correspondence between what's displayed and the candidate names in the database inside?
Yes. So
the strings that are representing these things.
So the correspondence that we check is that the display is a one-to-one function of the contest number and the state of the selections that have been made, and so. Oh, so if you reorder them, so this is.
Yeah, right. The strings are just the usual ballot programming error.
Yeah. So this is. So I should mention that this is. So okay, so I think we assume that so there's some election definition file which specifies how the candidate name should appear, and the translation from that election definition file to the screen is correct, which I think is what you're alluding to, right? And so that
Common source of problems.
is that right? Okay, so I think we could attempt to apply formal techniques to it. You know, I don't if that were an automatic translation. Yes.
So a standard question is that we do all the work to formally verify the software.
Yeah.
How do I, as a voter or an election official, know that that's the actual software that's running on the DRE at the time voting takes place?
Right. So that's one of the issues that we don't handle in this work. Like I said, right. So you have to have some other mechanism of ensuring that what you verified has not been tampered with, and it's what's running on election day. So you know, that's one of the things that should be done, but we don't address in our work. Okay. Thanks very much.
Thank you for your flexibility.
Thank you very much, Josh. Pleasure to be here. So Josh asked me to talk about attacks on voting systems. And so what I did is I went through the literature and I picked out 4 attacks which I think are illustrative of different issues that come up with today's voting systems. This is not an exhaustive list by any means, but I will explain why I picked each of these in turn. So the first attack I'm going to talk about dates all the way back to, you know, Yoshi, your original paper with Avi and Dan and everyone and Adam. And this is, of course, sort of a critique of the software that was used in the original Diebold DRE. And as we all know, there are many, many problems with this software. But the one I want to mention today is the use of the encryption. So this was a case where the developers knew they needed some kind of checksum and some kind of confidentiality properties for vote records that were on the DRE. Unfortunately, the cryptography they chose was poor. So they started off using 56-bit DES, which perhaps at the time they designed it would be defensible, but then they defined a constant, an ASCII constant key that's common to all machines. And then for authentication, they said, oh, well, we know we need some kind of authentication check, so we'll go ahead and we'll use a 16-bit CRC. And as the paper notes, Doug Jones mentioned some of these issues in the 1997 report, but they were still present in 2004. And then for extra credit, there's a linear congruential generator with a comment in the source code saying, oh yes, as per applied cryptography 1996. So this was a vulnerability where the designers had some notion of what they really needed to do, then they went to a textbook and completely misunderstood how to do it. The next thing I want to talk about is the Harry Hursty attack. So this is different. It's not a DRE. This is an optical scan system. So as we heard about already today, you have these scans. They go into a machine, and out comes some total. And then we'll take a look at the total, and if it looks right, then we accept it. If it doesn't look right or if it's too close, maybe we'll hand count it. The question in this attack is, what is the initial state of the memory on the machine? So if you have 2 yes votes and 6 no votes, and you scan them all, and the machine starts off with an initial state of yes 0 and no 0, you should get an outcome of yes of 2 and no of 6. What Hursty noticed in this attack, which was kind of interesting, is that you could have negative votes on the original machine memory card. And then, if you could slip a memory card with this negative number into the stack of cards that was then used to initialize the machines, the initialization check that election officials did at that time was simply to print out what's called a zero tape, which would then say, okay, let's sum up the yes and no's and make sure they sum to 0 and print the results. If you add 5 votes to yes and subtract 5 votes from no, you get something that sums to 0. And then that, of course, completely changes the results. And the problem here, as you already talked about, was that even if you hand audit this, unless you hand audit the original tape, you might say, oh, well, it was just, the original memory contents. You might say, oh, well, maybe it's just human error, or maybe it just got recounted wrong. You wouldn't necessarily, you may or may not notice that this is a problem in the machine. Then the third attack is something that came up in the California top-to-bottom review. So we're progressing through time here. The original attack I mentioned is from 2004. The attack that Hursty discovered was in 2005. This is from 2007. So this is a Sequoia direct recording electronic with a voter-verified paper audit trail. So you walk up to the machine, and it turns out that this particular machine will honor autorun.inf, which is a mechanism in Windows for automatically installing software. And it turns out a standard USB stick could be used to install arbitrary software on the machine after the machine had been deployed. So this gets to the question of how do I know the machine is running the software that I verified in the lab? Okay, but fine, it's got a verified voter paper audit trail. This shouldn't really hurt us, except it turns out the procedures of this particular machine in California do hurt us in the following way. The attack goes as follows. You're the voter. You walk up to the machine, you cast your vote. The machine prints the receipt on the VVPAT. And you see it, you say everything's fine, and you leave. But then the machine prints voided, as if you had decided to void this vote and then go back and recast. So there's this fleeing voter procedure which gets triggered in this case, where it looks like the voter went to the machine, edited his or her vote, and then just left the building. And the election official, apparently, according to the report, is allowed to come in and finalize the vote of the fleeing voter. The malicious software can change this vote, and because of the privacy concern over the election official not being able to see the vote of the voter, there's no way for the official to tell whether the VVPAT that gets finally printed and committed to the log is the thing the voter actually meant to put out. So the problem here is that even though we have an audit mechanism, the mechanism interacts badly with a procedure that was put in place to protect voter privacy, and malicious software, which can be introduced post hoc, can actually take advantage of this mismatch in order to create an audit trail that looks perfectly reasonable, but in fact is not what the voter intended. And then the final attack, this is allegedly discovered by some election officials in Kentucky. I say allegedly because they're under indictment right now. And so this description goes credit to Matt Blaze for a photo and blog post describing this attack. This is a picture of an iVotronic machine. It has a big button at the top that says vote. I would think, many people would think, if you push that button, it casts your ballot. So here you go, push the button. And actually, it goes to a confirmation screen. So you push the button, and it doesn't actually cast. It says, OK, are you sure you want to cast? And you have to push another button on the terminal itself to actually cast your vote. Apparently, there's a yes button on the screen. So here's the attack. Step 0, become an election judge. Or, yeah, as we heard, people are dying for election help. Step number 1, tell people that when you push the big red button, that's all you need to do, and you can leave. Pay no attention to the big yes button that appears on the screen. Many of them will believe you. Step 2, sneak over to the voting machine after they leave. See if they believed you. If they did believe you, you can just push the back button and change the vote to the correct value. And step 4 is profit. So these officials in Clay County, Kentucky, are alleged to have sold elections by doing this. And what was interesting about the report so far is that they appear to have discovered this property as early as they got the first machines. And this isn't a property that was missed by researchers who actually looked at this. So if I had to boil these all down into sort of one sentence as to what went wrong in each case, I would say in 2004, again, this is not the only problem with the Diebold DRE by any means, but one of the problems was we had this sort of textbook crypto problem. You had people who they knew they needed something, they went to a textbook, and they got it wrong. In 2005, we had an insufficient initial state check, that there's the procedures people had at the time. They thought they were checking that the machine had a clean initial state, that it didn't have any votes left over from previous contests in its memory. But the check they used didn't take into account this devious ability to put in negative numbers. And you could argue as well that the ability to have negative votes is a bug, not a feature in a voting machine. In 2007, the problem here is that the fleeing voter protocol interacts badly with the ability to add software to the machine after it's tested and certified. And that fleeing voter protocol ends up interacting badly with the audit trail. And then finally, in 2009, the fact that you have this bad user interface where the vote button doesn't do what you think it does, combined with the fact that people training voters are corrupt, leads to this attack. So the thing is that I found when looking at these attacks and other attacks like them is, what are the commonalities? Ideally, we would see some commonalities between vulnerabilities that would allow us to target the kinds of proposals that we all love and say, look, here's a class of attacks that we can get rid of. And so, for instance, we want to have vulnerabilities that fall into the category of software security, because then we can say, if we don't have to trust our software, we don't have to worry about those. Well, these are not all software security problems. We might say, okay, maybe the problem is direct recording electronic. If we went to something where we had hand recounts or we had an audit trail, we would be able to get rid of many of our problems. Well, they're not all direct recording electronic problems. Now, and while human error is a big deal in all of these cases, especially the last one, they aren't all human error problems, because the first issue of cryptography is something that no human could ever determine just by looking at the machine. And then finally, they weren't all discovered by trained researchers. The iVotronic attack was discovered by election officials who immediately decided to use it for personal gain. And Matt Blaze points out in his blog entry that this is something that had been looked at, a system that had been looked at by trained professional security researchers, and then totally missed this particular problem. So the question I have, and I would like to sort of pose to everyone here, is since we're going to be talking about new ideas for voting systems, what do vulnerabilities like this have in common? They don't have to have everything in common. There's no silver bullet. But when we're proposing new systems, what are some of the key things that we need to think about when evaluating or designing new systems? So with that in mind, I thought I might spend the last little bit of time sort of asking people if they had thoughts on this, and then we could put that into the slides for use later. So, sorry?
Are you also, like Sanjit, giving another talk?
No, I'm not, actually. No. This is like more of a record thing. So, yeah. Ben, I'll pick on you first. What do you think?
Fair enough. I think the first thing it means that this is a particularly hard problem.
Okay.
It's kind of an easy one, but I think it's a human one. It's one we forget.
You can pull the whiteboard and whiteboard right?
Oh, sorry, I should be more clear. I think that verifying elections, auditing an election in the face of voter privacy requirements is particularly hard.
So,
yes,
yeah, I actually do have a comment. I mean, it's mostly motivated by your last one. I mean, this is for somebody like me, who's a very technical person who looks at these things. I mean, I look at my knee-jerk reaction is dismiss this as human engineering, right? But I don't. Let's see. I don't want to sound quite so cynical. I think it's important. I think it needs to be solved. But here's what's missing: is nobody yet, to my knowledge, has ever put down a firm model of what constitutes a fully operable human being, right? and until you do that, we're never going to know whether we solve this problem. This thing is that issue has been a matter of shifting sand for as long as I know, and I mean. I think that intuitively we all agree that there is a human being who eventually devolves, close enough to incapable that we're going to have to accept that we cannot deal with those people, right? And I don't want to say that we should set that bar really high, but somehow people are going to have to say those people cannot be expected in all cases to interact what we would intuit to be correctly with, and just accept it and say, okay, but our system is good enough to meet 99.99% of the population's capabilities. When we get there, then you can say that you've maybe dealt with the human engineering problem.
Diebold?
I believe Microsoft has a regular cycle of testing on users that are selected to be naive users. They're known as the virgins. After a while, you have to get new ones for obvious reasons. And
and that's good and that's important, right? The elections. My point is that elections are so political, and you run into these problems of people all of a sudden pointing fingers after the fact. You're never going to have a situation where you feel you've solved the problem until you decide what is the minimum bar for naivete, right? I mean, you can't simply say, well, I've designed the system here, and then go get a stupider voter, right? You know, who isn't able to interact with the system.
yeah, but you don't start with criticize.
Adam has something he wants to say. Adam?
I'd like to object a little bit to your assertion that these voters are stupid. None of these.
I tried my best to make any shortcuts. No, they're not stupid.
You know, these systems are complex, and I think part of the problem is the lack of consistency between what we ask people to do.
I don't think you heard what I said. I agree, and I'm not saying that all voters are stupid. I'm not trying to characterize people at all. That's not the point. But the point is that there is some minimum level of capability that we are going to agree that we're going to address, okay? Beyond that, you can't hope to, right? I'm not asking that these systems be designed for computer science PhDs. That's not the point, right? And they should be designed for as broad a spectrum of society as we possibly can, okay? Absolutely. And if you can define that and put boundaries around that broad spectrum of society, and show that a system doesn't meet the requirements of that broad spectrum of society, then I will say that system has failed. That's fine, okay? But put some boundaries around what that spectrum is, right? My dog is very smart. Does it have to meet his requirements? Right? That's my point.
Any other comments or things people want to put up here for later?
I'm going to throw in something ambitious, and that I guess I have a sense of this sort of ad hoc approach that we've taken in the past hasn't proved to work particularly well, and maybe we need new paradigms. That's sort of the self-serving entry for verifiable paradigms as a completely different approach that can solve a lot of these problems.
Any other comments people want? I mean, this is going to be something I hope we'll be able to use later on, which is why I put up here. Yes, Ron?
I think I don't find the search for commonalities useful.
Okay.
I think that these are very complicated systems with many different aspects and dimensions in which they work. And, you just have to expect to look at these kinds of systems with many different kinds of approaches. There's human protocol approaches, and there's software engineering approaches, verifiability, everything else. So it's trying to take very different things and find commonalities. That's not what I find that useful.
Okay, great. Thank you. All right. Well, thank you very much, guys.
Great. Thank you. Okay. Great talk.